Thank you very much. Good afternoon to everybody. My name is Katarina Karl'ova. And first, let me thank to the organizers, Marcelo, Socorro, Luan, as well as Jordana. They invited me here to speak about our results. I will speak today about mixed spin Heisenberg octahedral chain. And here is outline of my presentation. After brief theoretical motivation, I will introduce the studied model. Then I will present it the ground state phase diagram, as well as results for magnetization and in magnetization curves in zero temperature, as well as non-zero temperature and thermodynamics as well. And at the end of my presentation, some conclusions and future outlooks will be offered. I will speak today about fully quantum Heisenberg model, which can be in general defined through the following Hamiltonian, where first term is interaction first term is nearest neighbor interaction, which depends on operators Si and Sj, and the summation runs often through the nearest neighbors because exchange integral J depends on how overlap orbitals, and these overlap decrease with the distance. That's the reason why other interactions can be neglected. And the second term is magnetostatic energy of magnetic moments in external magnetic field J. Heisenberg octahedral chain is a frustrated model, and geometric frustration can be explained, for example, on these three interacting spins, which interacts with antiferromagnetic interaction. And geometric frustration means that not all spins or not all interaction can satisfy antiparallel orientation. Besides that, there exists also frustration of antiferromagnetically interacting spins in effort to create valence bond, as known as singlet dimers. And frustration causes often a lot of interesting features, which can be seen also in magnetization. For example, I can mention here in magnetization curve at zero temperature, it can be seen as magnetization plateau or magnetization jumps and steps, or quasi-plateau or magnetization ramp, or cusp, kink, or spin liquid. Now let me tell you why is interesting to study such kind of systems from theoretical point of view. Probably the most interesting findings was the discovery of exotic phases. For example, this kind of phase, Affle-Kennedy-Liptak-Tasaki phase, which is the special case of Haldane phase, was one of the interesting quantum states. And how to imagine it? So you can imagine it that in a linear one-dimensional chain, you have spin 1, atoms, and spin originates from electrons which have spin 1/2. So each spin 1 can be seen like 2 spin 1/2. And the phase is created such that way that each atom, spin 1, creates singlet pair with the nearest neighbors from the left and from the right, and it created these singlet pairs along the whole chain. And what is the most interesting, that in open chain, at the edges, there is only one neighbor in which spin can create singlet bonds, and therefore there is one unpaired spin. And from that point of view, if we have, for example, this Heisenberg chain created from nickel 2+ cations, then on the edges, this chain will behave like copper 2+. And that is not trivial feature. The other exotic phase, which I will explain here, can explain the last plateau which was measured for this compound. And here is a magnetization curve measured up to the ultra-high magnetic fields. And this last plateau can be explained by localized magnon, which is shown. This experimental realization is experimental realization of Kagome lattice. And this last plateau can be explained by localized magnons, which is shown by this red ball. And these signs tell us about amplitude probability. And this magnon, it means that if you flip one spin on hexagon, so it is delocalized, but it cannot escape from the hexagon. So it's localized on hexagon. And the most dense packing of these magnons really leads to the 7/9 plateau which were measured for this compound. So even if Heisenberg model is known almost century, we still do not have a strong procedure which will allow us to solve Heisenberg systems in general for zero and non-zero temperatures. So let me now briefly summarize how methods we can use from numerical points of view. In order to obtain some results for zero temperatures, one can use Lanczos algorithm, which is okay, but it can work roughly up to 50 spins, which can be still far from the reality. This Avogadro constant 2 to the power of 23. And the other method which one can use is density matrix renormalization group, which can be used for the larger system sizes, but it will be not exact anymore. And at non-zero temperature, one can use full exact numerical diagonalization, but it is worse than Lanczos method in means of system sizes, because one can use it only roughly up to the 40 spins. And if you combine it with finite temperature Lanczos method, so you can increase the system size, but still roughly up to the 50 spins. So the other methods which can be used for, which can work for larger system sizes is quantum Monte Carlo, which is a strong method for quantum systems, but it has also some limitations because of frustration and sign problem. And how Andreas told us Monday, it can be avoided by using the dimeric basis. But it is also valid only for some special systems, not for everything. So as you can see, we still do not have procedure which will be covered for like everything for quantum spin systems. So, and my question is it possible to calculate something for quantum spin systems, fully Heisenberg quantum spin systems, by using only paper and pen? So I hope that my presentation particularly will answer this question. So let me introduce the studied model. We have studied the mixed spin 1 and spin 1/2 Heisenberg octahedral chain, which part of which can be seen on this figure and which can be defined through the following Hamiltonian. And okay, so we have considered monomeric spin 1 particle, which are interacting with spin 1/2 particle from square placket by antiferromagnetic interaction, and also interactions between nearest neighbor of particles from square placket interact with antiferromagnetic interaction. N here in Hamiltonian is a total number of unit cells, H is magnetic field, and N involves 5 spins. So in one elementary unit is 5 spins. Okay, in order to find ground state in highly frustrated parameter region when J2 is greater than 3J1 in a zero magnetic field, we have used variational approach, which this method lies in fact that Hamiltonian can be decomposed in cluster Hamiltonians, and these cluster Hamiltonian are related to the Heisenberg octahedra. And this method then allows us to obtain lower bound for the lowest energy state of Heisenberg octahedral chain, which is in this case the sum of the lowest energy state epsilon J0, lowest energy lowest energies epsilon J0 for a single octahedron, and single octahedron can be the energy spectra of single octahedron can be found through the simple Cambe projection method, and it depends on total spin and total spin on square placket and some composite spins. And according to that, one can find in highly frustrated parameter region the ground state, which has a character of monomer tetramer state, where monomeric particles are free and each square placket creates a singlet tetramer state. in order to find a ground state just below the saturation field, we have used localized magnon theory, which can be used as follow, that one need to find all eigenstates from the basis ket ij, which is one spin deviation on a fully background ferromagnetic state. And according to these, one can solve eigenvalue problem and obtain 5 energy bands, which are shown in these figures. And if J2 over J1 is greater than 2, then the lowest energy will be flat band with the energy, or the lowest state will be flat band with the energy epsilon 1, given by this vector with the character of one magnon state on square placket, and localized character of this one magnon state can allow to create one magnon states on each square independently, and the lowest energy eigenstate of octahedral chain will be bound magnon crystal phase with the largest possible number of bound magnons on octahedral chains. It means on each square placket will be one magnon state. Okay, in order to find ground states in a fully parameter space, we have used DMRG method and Lanczos algorithm for effective mixed spin chains, using the fact that the total spin of square placket commutes with the Hamiltonian, which can obtain quantum spin numbers 0, 1, or 2. And according to that, each square placket can be substituted by 1 with the given total spin. And we have compared energies of all possible effective mixed spin chains in order to obtain ground state phase diagram. And in our case, ground state phase diagram will consist from the effective Heisenberg mixed spin chains of these 7 effective Heisenberg mixed spin chains. And here is already a ground state phase diagram in zero and non-zero magnetic field. And interestingly, ground state phase diagram in zero magnetic field is rich on unconventional ground states, as for example, 2 ferrimagnetic states of Lib-Lattice type, then uniform cluster-based Haldane phase, then uniform Haldane phase, then 3 cluster-based Haldane phases, and monomer tetramer phase. And in a non-zero magnetic field, beside these, there is also 3 areas of spin liquid phase and bound magnon phase corresponding to 2/3 plateau in magnetization curve. Okay, on this figure is shown how we can understand the cluster-based Haldane phases. The clusters in shades ovals are in triplet state, which are fragmented by tetramers in singlet state, because singlet tetramer breaks correlation on both its sides. So, and here is given periods. So it means that if each square is in singlet tetramer, so we can see it like cluster-based Haldane phase with period 1. If every second square placket of octahedral chain is in singlet tetramer, so it is like this is okay. Tetramer, hexamer tetramer state, it's period 2. Okay, and also in language of effective mixed spin Heisenberg chain is, for example, 1110. It means that monomeric particles have spin 1. Then this square is in triplet state, and next square is in singlet state, so 0. Okay, in order to confirm our results, we have also performed DMRG simulations on original octahedral chain, and on the right-hand side, you can see a local magnetization where these small red squares is local magnetization of 4 spins of a square placket. And this also confirms how cluster-based Haldane phase looks like, because as you can see, for example, for this 1/6 plateau corresponding to the hexamer tetramer phase, each second square has local magnetization 0. What does it mean? That each second square does not contribute to the total magnetization. And here is zero temperature magnetization curves for several cuts of parameter space. And for example, if J2 over J1 equals 1.5, one can find in zero magnetization curve Haldane phase, then Tomonaga-Luttinger spin liquid, then two plateaus, 1/6 and 1/3 plateau corresponding to the Lieb-Matisse ferrimagnetic state, in which every second or every first square placket was substituted by total spin with number 2. Then is other spin liquid and fully polarized state. So as you can see, it is rich on phase transitions, yes. And if J2 over J1 equals 2.25, there is a lot of, one can find in this magnetization curve a lot of plateau. For example, 1/12 plateau, which is very, very tiny, corresponds to the cluster-based Haldane phase with period 4, 1/9 plateau to the cluster-based Haldane phase with period 3. So each third square is in singlet tetramer. 1/6 plateau to the hexamer tetramer state, and 1/3 plateau to the monomer tetramer state, and 2/3 plateau to the bound magnon crystal phase. And I forget to say that these results were obtained from DMRG, from the effective Heisenberg chains, as well as from the Lanczos method on original Heisenberg octahedral chain, and they are in good accordance. Okay. In a highly frustrated region, as well as in moderate frustrated region, one can describe thermodynamics by the use of effective lattice-gas model, and the idea is as follows: that one magnon state and two magnon state can be substituted by monomeric particles, or triplet hexamer state can be seen as dimeric particles. And then the effective Hamiltonian was created as follows: that from the fully polarized ferromagnetic state, we have subtracted the energies of this kind of particles, which are given by the chemical potentials, which are given by the difference from their own energy and from the energy of the fully polarized state, and the presence of absence of this kind of particles are given by the occupation numbers. We have also assumed Haldane phase as one particle which is spread along the whole chain. And according to this, one can write the partition function, and from which can be calculated all thermodynamic quantities. Partition function also have projection operators. Projection operators which forbids double occupancy with more than one particle on, for example, square placket. Okay, here let me remind the ground state phase diagram and explain our lattice gas description from the different point of view. So if the J2 over J1 is greater than 2.16 is here. So the most relevant ground state is fully polarized ferromagnetic state, then bound magnon crystal phase, then monomer tetramer phase, hexamer tetramer phase, and Haldane phase. It is necessary to say that these two tiny phases, which correspond to the 1/9 plateau, and this blue line to the 1/12 plateau, were neglected in our lattice gas description. And our lattice gas description was developed on the idea that above these phases at finite temperatures, for example, each square placket of octahedral chain can be either fully polarized or be in one magnon state or two magnon state, or can belong to the triplet hexamer state or to the Haldane phase. Now let me show you our results for J2 over J1 equals 2.7, where 2/3 plateau, 1/3 plateau, and 1/6 plateau are expected. So here is magnetization, susceptibility, and entropy as a function of magnetic field for unit cells it means 20 spins, and on the lower panel, the same for 6 unit cells, it means 30 spins. And our lattice gas description were compared with the full exact diagonalization for 4 unit cells and exact diagonalization with combination of finite temperature Lanczos method for 6 unit cells. And as you can see, lattice gas description, which I introduced just few minutes ago, is in perfect agreement with the full exact diagonalization, and it can be also seen that susceptibility is in perfect agreement for 4 unit cells. Maybe for 6 unit cells, there is small discrepancy in this parameter region, and entropy, which is more sensitive for thermal fluctuation. So it's not, there are some discrepancies for higher temperatures, but still at very low temperature, it fits perfect. Okay, our lattice gas description also includes Haldane phase. So it should explain also zero magnetization plateau in, for example, in parameter region J2 over J3 equals 2.3. So here would be zero plateau. And indeed, as you can see, our lattice gas description matches zero plateau perfect here for 4 unit cells, but here for 6 unit cells there are much more discrepancy because of what I said before. It is some indication that what exact diagonalization with combination with finite temperature Lanczos method found 1/9 plateau, which is neglected in our lattice gas description, and it cannot appear for 4 unit cells because of 4 unit cells is inefficient system size for existence of this kind of high period ground state. So also full exact diagonalization cannot find 1/9 plateau for 4 unit cells, but of course here must be some discrepancies because our lattice gas model neglect this state which corresponds to the 1/9 plateau. But still at higher fields, our prediction fits perfect with the full exact diagonalization as well as combination of diagonalization and finite temperature Lanczos method. And at very low temperature, it seems perfect as well. Okay, to see inside the finite size effects, we have plotted here entropy as a function of magnetic field for 3 different system sizes. And as you can see, at high field region, there is no finite size effect for these systems, only in for small fields, there are some finite size effects, which persists up to 2.25 magnetic field. And the system size is bigger, then the entropy is smaller. And as you can see, what is also very nice that even or okay, either full exact diagonalization and exact diagonalization with combination of finite temperature Lanczos method can give us some results for system which is a small system size. But our lattice-gas description allows us to give us some predicts also for thermodynamic limits. Okay, and here is my last result, which I will present today. I don't know how much time I have. It's okay. Okay, so here is entropy as a function of temperature for two different magnetic fields. We are here in this green region. So just below the critical field and just above the critical field is 0.3. So just below I have used 0.25 and just above 0.35. And just below the critical field, the ground state is hexamer tetramer state, which is a twofold degenerate ground state. And indeed, entropy at the limit of zero temperature approaches this value. Also, our effective model confirms that. And as the same for 6 unit cells. And above the critical field, when critical field is 0.35, so the ground state is a non-degenerate monomer tetramer state, and indeed entropy goes to zero at zero temperature. And from these figures, one can also see validity of our lattice-gas model. And for example, for the entropy, our lattice-gas model predicts well numerical data up to roughly 0.05 temperature. Okay, let me conclude my presentation. So we have studied mixed spin 1 and spin 1/2 Heisenberg octahedral chain, which has a rich ground state phase diagram, including cluster-based Haldane phases. And we have offered a description of low temperature thermodynamics through the classical lattice-gas model. And what can be also extended for the other models, for example, for diamond chain, what Joseph was presented today in the morning, or sorry, not diamond chain, diamond-like decorated square lattice, or also other model like diamond chain or octahedral chain with other spin system with other spin values. And also it can be extended, for example, to be more precise, one should involve hardcore trimers and tetramers, which are related to 1/9 and 1/12 plateau also in our models. But the problem is that it cannot be more analytically solvable, exact solvable. Okay, so I would thank you for your attention, and my last comment is that the first part of my presentation was already published with my co-authors Josef Strečka and Taras Verkholiak in 2019, and the second part of my presentation should be published soon. We already received positive judgments So this still is in a review process. So again, thank you very much for your attention. Okay.
Okay, Katarina, thank you for our presentation. Let me just stop for now. No, no, I don't need it. Okay, I open the opportunity for questions. Here, the shuttle here. Anyone in the chat have some questions? I don't think so. So, okay, I have a question. You demonstrate some results from exactly the organization, right? For 4 and 6 unit cells.
Yes.
Equivalent training interdistinct, right?
Yes.
Then you demonstrate the results of what you expect in the feed size limit, in the thermodynamic limit. You have that curve for the entropy. How you reach that prediction for in the thermodynamic limit?
How we get prediction for the okay, so I had there the partition function, which also from the partition function can be calculated all thermodynamic properties. Yeah, for example, free energy and so on. And the partition function was solved by transfer matrix. And for solve thermodynamic limits, you know that you just need to use the highest eigenvalue of transfer matrix, but for the finite systems, you need to use all eigenvalues of transfer matrix in order to compare it with the finite size systems which were obtained by exact diagonalization method.
I see.
So there was like 2 procedures which were split on the level of free energy, how were calculated for finite systems and for infinite systems.
I see. So it's the comparison between 2 numerical results with the one analytical prediction, right?
Plus one numerical is 2 numerical is numerical.
Yeah.
For 4 and 6 units.
Yes. And about your expectation about the Haldane state, how that became a edge state protected by symmetry, right?
Okay, there is I didn't say during my presentation that we have assumed periodic boundary conditions, so there will be no edge space.
I see, yes.
Yeah.
Exactly what I
But within this cluster-based Haldane phase, it can be seen from the local magnetization that something like protected edge states there can be seen actually. I don't know if we share still our presentation.
Which page?
Okay, in local magnetization, this yellow figure, you can see this is, for example, this 1/9 plateau corresponds to this state. And this state is fragmented by tetramer from the left and from the right. So it means that it will be open chain. And in language of mixed spin Heisenberg chains, it will be open spin 1 chain, but with small systems size. Yeah, but local magnetizations seems that and this shade yellow part tells me about this cluster, and on the left and right I have higher local magnetizations of monomer spins than in the middle, and which will be the system size greater. It seems that, look, here in the middle, local magnetization decreases, while in the corners stay constant. So it will be farther and farther with the system size, it should gain this protected Haldane phase, but still we have asymperiodic boundary conditions, so it will be all zero.
Yeah, yeah, states don't emerge naturally. Yes,
Yeah.
that was the question. Because you see that they have in phase, but when I see that image, say, okay, should be edge state. So maybe he considered periodic boundary condition. What's explain everything.
Yeah,
Yes, I see.
my
No, there's no problem. No
regret
worries
that
about
I
that.
didn't say it.
Okay, any more questions?